So this is Jiayi. So I'm a postdoc, currently a postdoc at McMaster University, partly supported by CETA through a national fellowship. So before going into my talk today, I just want to quickly mention another paper I worked on with the Thanks collaboration. So this is just a new paper that I put on arXiv last Monday. The title is Star Formation Laws and Efficiencies Across 80 Nearby Galaxies. And I think the goal of this paper is try to provide a recent update, a pretty good update on a lot of previous works in this field by looking at a very large set of homogeneous data and use uniform methodological treatments. We also tested 6 different ways of determining the star formation rate and the molecular gas mass, just to make sure that we understand our systematics and get the most reliable results we can. So if you're interested in star formation laws, star formation efficiencies over a lot of galaxies, please check out this paper. Now, this will not be the central topic of my talk. The central topic of my talk is actually the formation of massive star clusters. So I just want to give you a quick motivation for this. So these kind of objects are usually defined to be above 10 to the 4 solar masses in their stellar mass, and the more massive ones can be above 10 to the 5. I think these objects are really cool and unique for 2 reasons. First of all, they only form under very high gas density and pressure conditions. And these kind of conditions are actually more common for star formation at high Z or in early universe. So by studying these massive star clusters, we'll actually be able to constrain the physics of star formation and feedback in very extreme conditions that are more characteristic of the early universe. The second thing here is that these kind of massive star clusters, especially the younger ones, are possibly the closest analogs you can find for forming globular clusters in the local universe. Although how similar they are, in fact, are still under a huge debate in the field. But I think it's fair to say that these are the closest you can find in our neighbor, and you can actually resolve them. So if you study them well, this can probably shed light on the mysterious origins of globular clusters. So studying these things seems important then, but there are quite a few challenges for actually doing this. I think the core issue here is that the formation of these massive clusters is just very fast. It appears in the very beginning phase of a cluster evolution, and it just happens really fast. And this means several things. First of all, this means these kind of forming objects are actually really rare. So if you actually count the number of forming massive clusters, especially those above 10 to the 5 solar mass in the Milky Way, there are possibly just 3-ish. And if you count everything above 10 to the 4, there may be a dozen or slightly more than that. But with that small number of statistics, you cannot do much. So you really need to look beyond the Milky Way. But that actually poses a challenge for observations because these kind of things are small. So it's really hard to resolve them. The second thing here is because it happens at the beginning phase of cluster evolutions, they are still being hidden behind a lot of dust. And this creates challenges for short wavelength observations, especially in the optical, where there's very little hope that you can catch them. And even in the infrared, sometimes it's hard to see them at shorter wavelength. And finally, again, because this still happens in the very early stage of cluster formation, the clusters do possess a large gas reservoir. And this means that you can't only look at the stars to tell how the cluster will evolve, because what the stars are doing to the gas and what the behavior of the gas is actually makes quite a difference in terms of how the cluster will evolve in the future. So all these 3 challenges actually point to the same direction, which is ALMA, and I'll explain why. We need to look beyond the Milky Way. And ALMA is great because ALMA can offer really high resolution and very reliable imaging that is, not comparable for, not paralleled by other telescopes at similar wavelengths. Behind a lot of dust, ALMA doesn't care about that because it's long wavelength observation. So we can really provide with ALMA some like unextincted information of the formation of these objects. And finally, for tracing the gas reservoirs, there's a rich set of gas tracers in the millimeter. So ALMA, again, will be wonderful for doing this science. So this is exactly what we're trying to do with this project, is to use ALMA to look for the forming young massive clusters in the nearby galaxy. And this galaxy is NGC 3251. So this is a relatively nearby 10 megaparsec-ish galaxy. It's reasonably massive, comparable to the Milky Way, and it has a very strong bar going this way. And this bar is funneling a lot of gas from the outside of the galaxy towards the center and creates a prominent central starburst ring highlighted here. As you can see from this Hubble optical image, the ring is dusty. It holds a population of optically visible clusters and possibly also a population of embedded clusters in those dusty regions. And if you add up all the star formation rate of this region, is about 0.6 solar mass per year. And this radius is actually just 500 parsec. So you're actually packing up a lot of star formation within a very small area. And this means that the gas density is high, the star formation rate is high, and this is exactly the environment we believe that young massive clusters would like to form. So this is the area of interest in this work. This galaxy also allows us to do a quite extensive multivariate synergy. So we have ALMA data for this that can give us a rich information about the gas, the dust, the H regions. We also have existing HST data, and this really allows us to trace all the exposed starlight from the clusters. And finally, very exciting, we will have observation for this galaxy with JWST next month. So JWST will be wonderful in providing like tracers for the attenuated starlight, so we can actually look deeper into the dust, and we can also trace the hot dust and the pH. So all in combination, this will be a wonderful multivariate project for studying this young massive clusters. Now, I will explain a little bit about what the ALMA data looks like. Since this is an ALMA conference, I can probably go into slightly more technical details. So we are targeting a rich set of tracers in both band 3 and band 7. This includes the band 7 continuum, which mostly tells you about the thermal dust continuum from the objects. The 93 gigahertz band 3 continuum is mostly free emission from the ionized gas around those young massive clusters. We also have as a bonus a very deep and high dynamic range CO32 imaging. So this tells you where all the bulk gas is. And on top of that, we have a lot of high critical density molecular lines, including HCN, HCO+, and CS. They tell you where the dense gas is within and around the clusters. The data resolution is about 0.1 arcsecond or 5 parsec-ish for CO32 and 0.17 or 8 parsec-ish for everything else. The difference between those is just because we're using a different weighting scheme as supported by the different brightness of the things. But I would like to say that this is really pushing the boundary of extragalactic observations so that we can finally connect with some of the things we can already achieve in the galaxy for a while. And just to say that in order to make sure that we cover all the emission on all spatial scales, we're combining 3 ALMA configurations for each band, just to make sure that this is reliable imaging. Now, with this awesome new data, we are trying to answer 3 big questions for the interesting dots that we see in the continuum images. And the questions are, what are these objects? Where do they come from? And where they're going? So as you can see, this is basically like the 3 philosophical questions that we always ask for ourselves, but now we're asking for these kind of objects. The first question is what they are. And the upshot is that this is actually a population of massive, compact, and embedded forming clusters. So if you look at the continuum in band 7, just 350 gigahertz. So as I said, this is mostly thermal dust. If you assume a dust temperature of around 130 K, which is typical for the dust near forming clusters, you get a gas mass of 3 times 10 to the 4 to 4 times 10 to the 5 solar mass. And if you assume a lower dust temperature, this number will be higher. So this is telling us that there's a lot of gas for each of those dots. And if you convert a substantial amount of that gas into stars, you will be creating massive clusters. If you look at the 93 gigahertz continuum, which tells you mostly about the free from the ionized gas, and if you assume that all those gas are being ionized by a stellar population of around 5 million years, which is basically the overall stellar age for this entire region, you get a stellar mass of 1 to 5 times 10 to the 5 solar mass, again, for each of those dots. So that means for those dots, there's already a pretty massive stellar population there. So what we're really looking at are actually massive clusters in their formation. Now, if you look at the source sizes, you look at the half width, half max, which is basically the half light radius for each object. It's around 1 to 8 parsec. So they are really compact. And this is comparable to young massive clusters people have found with with other nearby galaxies in shorter wavelengths. And finally, I want to highlight that if you actually compare the location of these objects with a Hubble image, you'll see that among all the 18 sources identified in both bands, only 4 of them are co-spatial with an optical object. So this means that these objects are really deeply embedded in the dust. Now, having answered what they are, now let's talk about how they came into being. This is actually a pretty hard question to answer, but I think some interesting insights can already be gained if you just look at the spatial distribution of these sources. So if you look at the spatial distribution, you'll notice that most of these sources clusters towards the northern and southern end of the ring. And this is interesting because these two regions are actually where the large-scale gas inflow driven by the bar, the slider bar, is flowing in and hitting this central ring. So that creates a very interesting condition near these two spots. And this kind of spatial distribution for the YMCs actually can allow us to differentiate between two cluster formation scenarios that have been in the literature for a while. So the first is the so-called popcorn scenario, which means that you are just piling up a lot of gas in this ring, and YMCs are just going to form randomly along the ring because of gravitational instability, because the gas cannot just be there forever, right? So that means you will see a nearly random distribution of young massive clusters just along the ring. Which doesn't seem to be super consistent with what we are seeing. The alternative scenario here is that it's so-called pearls on a string. So the idea being that a YMC formation actually triggered spatially at some particular location, and then they move further down the stream. And this is actually more consistent with what we are seeing, and especially given that the gas are inflowing at these two regions. And also all the sources are just moving along this ring, and there will be passage of different orbital locations like pericenters, which might be important for dynamics. So we conclude that this might be more consistent.
3 minutes.
Thank you. Right. So we conclude based on our data that the young massive clusters, most of them might form due to some external triggering mechanism by either gas inflow or pericenter passage. Now, the last question I try to answer here is where they're heading. We know that the cluster formation will not just last forever, because either they're going to completely exhaust all the gas they have, or when stellar feedback turns on, they are going to clear the gas for the clusters. And we also know, based on a lot of research in the literature, that the effectiveness of a lot of different feedback mechanisms, including photoionization, radiation pressure, and supernovae. So they depend on the mass and size of the star clusters themselves. And more specifically, some of them depend on the surface density of the gas, some of them depend on the total volume density, etc. And so by looking at the mass and size distribution of the clusters we see, we can actually gain some insight about whether feedback will be important for those kind of objects. So now if you focus on these things in the right-hand side panel, so the things that are, this empty dots, so those are the young massive clusters we found for this galaxy. And if you look at their distribution, most of them locate within this shaded area. So that means most of these clusters are still very susceptible to these kind of feedback processes. So once feedback turns on, meaning that once they form a substantial population of young massive stars, and sometimes later supernovas start to explode, the gas won't be there anymore. So the gas will be just driven away, and the cluster formation will be shut off. So this is likely what's going to happen for these objects. One last thing I just want to mention, there's a caveat here, which is the measured sizes of these YMCs. We know that they depend quite sensitively on data resolution. So if you look at the literature and look at objects being observed with lower and higher resolution, you see that the higher resolution observations usually tell you that the YMCs are a little bit smaller. So this might also happen for our sources. So our sizes might be taken to be more like upper limits of the sources, and they might actually move down. And that might be more interesting because they might actually form without much of the feedback being efficient for them to clear all the gas. And this will be something we are actually be able to test with an approved cycle 9 observations, which will improve the resolution by a factor of 3. All right, so I think I am basically using up most of my time, so I'll leave the summary slide here and happy to answer any questions.